Hello, this is Chuck Ridgway. It's Tuesday. It's time for another Tuesday live stream. Today's topic is all about analog filtering techniques. Now, as many of you know, analog signals are an important part of a lot of control systems out there, certainly in the process industry and other industries as well. Today, we're going to talk about different techniques that we can use as control engineers to filter those signals so we get the information back that we need at the appropriate rate with the appropriate stability. And joining me today is Mr. Casey Gardner. How you doing today, Casey?
Hey, not too bad. How's it going, Chuck?
It's going great. Now, as our lead sales engineer working with new OEMs, you talk to OEMs in the design process, you talk to them as they're, implementing their systems on the floor, and also when they first get them into the field. When you have customers that may run into or be concerned about analog stability issue, what's one piece of advice that you could give those folks?
I would say we'd have to start back at their installation practice. That's one thing they've got to look through to make sure everything from the very beginning is actually installed properly. So things like cable length or wire gauge or proper shielding or proper grounding, all can affect those signals coming straight into the controller. So before we even think about any filtering options and logic or anything like that, we've got to start there. Absolutely.
So good filtering is absolutely no substitute for a bad design or installation practices for sure. Great, thanks for that. So today, of course, as usual, Casey will be manning the chat. If you have any questions, just chat those in. Casey will either respond directly or he'll maybe save your question for the end. If you're watching this on replay, which a lot of you folks do, you can still ask questions. Just chat there. Instead of chatting them in, just type them in the comment section. We'll get those answered in non-real time. Okay, let's go ahead and get started. All right, so analog filtering techniques. That's our topic for today. So let's take a look at our program. We're going to start by talking about why analog filtering and what Casey just mentioned, and that is that good analog filtering is no substitute for poor installation practices. We'll talk about when and where you should filter. We'll talk about the filtering that's available built into the OCS I/O configuration. We'll also talk about filtering that you can implement in Logic. We're going to talk about different types of filters. We're going to talk about low-pass filters. We're going to talk about the technique of sample averaging. We're going to talk about the technique of change limiting. And we'll talk a little bit about some more advanced filter options that are out there that you may want to implement in your application. And of course, as always, we've got plenty of demonstrations for you. Okay, let's dive right in. Okay, so why analog filtering? Well, as I mentioned in the opening, analog signals provide key feedback to the controls engineer as he attempts to design a control system for the machine or the process, whatever the case may be. And of course, it's important that the feedback you receive from the analog signals is representative of what's really happening in the control system with the appropriate response time so that you can monitor and control that system appropriately and with the appropriate stability as well. Now, it's not uncommon for the signal to be unstable and or noisy, or maybe not unstable, but less stable than you'd like, let's say, or more noisy than you'd like. So that is something that we need to address as control engineers. And as we've mentioned more than once now, every effort should be made to eliminate the source of instability and the source of any noise before we start the filtering process. Now, what are some of the sources of instability or noise? It really makes sense for us to talk about these a little bit before we dive into the filtering options. Well, one thing that people neglect sometimes, I know I'm an electrical engineer by degree and by practice most of the time, and sometimes I get in that electrical mindset and I don't think about the fact that there are mechanical things in a control system or a machine that can actually impact stability and noise of signals, including analog signals. So you could have, for instance, you might be monitoring, let's say, flow from a fluid, and maybe there are some mechanical issues with the piping or where the sensor is installed. Maybe there's turbulence issues, whatever the case may be. So you may need to correct that mechanical issue before you start worrying about trying to filter everything out electrically. And that's just one example of a host of different mechanical issues that could cause problems for an analog signal. And of course, as an electrical engineer, I'm always thinking electrically, and there's plenty of electrical issues as well we need to worry about. We could have electrical noise riding on the signal. And have we used proper wiring techniques in the analog signal chain to ensure that the impact of those is minimized? Did we select the right cable? Okay, with analog wiring, usually that means shielded, twisted pairs wiring. If we do have shielded wiring, did we handle the shield properly? Okay, if we've got shielded cabling and we haven't grounded the shield properly, then that shield is just acting as an antenna for our signal wire. That's obviously not what we want. So we're going to want to ground that shield at the best earth ground we can find, and preferably, if it's on the sensor side as opposed to the instrumentation side, such as the OCS side, that's better yet. Also, let's not forget cable routing. Okay, we want to route our signal cables away from our high voltage cables, and we certainly don't want them running side by side in a cable tray if we can help it at all. And when they do intersect, we want those to intersect at a right angle. So again, these are all the types of basic cable and electrical wiring techniques that we need to pay attention to before we start worrying about any kind of filtering techniques. However, there is a time and a place to filter. Once we've taken care of the installation and the design properly, now we may need to implement some filtering. So, in this topic, I know some of you, I guess it's feasible, may have seen the topic and thought that we might be talking about adding external capacitors and resistors and inductors to do analog filtering on our signals. But in reality, what we're talking about is digital filtering of those analog signals that are coming into the OCS. Okay, so this is effectively filtering that's performed after the analog to digital conversion is done in the OCS hardware itself. So that's the level of filtering we're talking about today. Now there's 2 points at which you can perform your filtering, all right? The first point is actually in the I/O configuration, okay? So the XL Series OCS, when you go to the I/O configuration, we'll show that in the demonstration portion, but when you go there, you can see as you're configuring your I/O, your analog I/O, you have the option to configure filtering for those analog signals, okay? And that's performed after the A to D conversion, but before that value is written to the %AI register. Okay, so that's done by the OCS firmware. And all we do as control engineers is we configure that filter. We set the severity of the filter, if you will. The second place you can perform your filtering is in your logic program. Okay, so that, of course, in that scenario, you're taking the AI value that came in from your analog to digital conversion, and you're going to take that AI value and you're going to perform filtering on that value and then create a new variable in your program that you're going to use in your control algorithm. Okay, so those are the 2 different places you can do your filtering, and we're going to, of course, show both. All right, let's start with a low-pass filter. And in particular, we're going to talk about a low-pass filter that is implemented in the OCS firmware as part of the I/O configuration in the OCS. Okay? So what is a low-pass filter? Well, a low-pass filter is designed to allow signals to pass that are not changing rapidly, but the signals that are changing rapidly at a higher frequency, it's going to attenuate those more. And in the case of the OCS, in the hardware configuration, you have the ability to set up an optional digital filter that will perform that level of attenuation. And the adjustment that you can make is effectively in setting a filter constant. Okay, and that filter constant can be set anywhere from 1 to 7. Now, if you set that filter constant at 0, effectively it's disabling any filtering, and therefore the OCS firmware will just do the analog to digital conversion of your signal and directly pass that into the AI register directly. However, if you implement the filter constant between 1 and 7, then it's going to perform that level of filtering instead before it writes the AI value. Okay, so now how does that filtering work? Well, let's take a look at a filter constant with a value of 1. So what that effectively means is that the OCS firmware is going to do the A to D conversion, and then it's going to compare the current A to D converted value with the previously stored AI value. Okay, and it's going to give each of those a weight of 1 or an equal weight. It's going to add those together and divide by 2. So with a filter constant of 1, the new conversion and the previous AI value have equal weight. Now, if you set the filter constant to a value of 2, now the previously stored AI value has double the weight compared with the new conversion. If your filter constant is 3, the previous converted value or the previous AI value has triple the weight of your new conversion. So that's effectively the algorithm that's used, and you can see it graphically shown on the screen where we have graphed response time or response percentage, okay, or response to a change on the y-axis, and along the x-axis that's in time, and in this case it's times in terms of logic scans, okay, or A to D conversion scans. Almost all of the OCS controllers with their built-in analog I/O convert those once per scan. Now that's not the case with the Model 6, but it's true with all the rest of them, okay? So for all of the rest of the XL series analog, except for the Model 6, your A to D conversions are equal to your scans. So as you can see, the lower your filtering value, the faster your AI register is going to get up to a higher value, but with the potential of noise, okay? So the more stable it is, but also the more slower responding, that's what you get when you have a higher filter constant level. Okay, so this is the easiest way by far to take advantage of filtering within the OCS, and that is just enable the filtering that's made available in the hardware configuration. Okay, so let's go ahead and show how that works now. So I'm going to go ahead and fire up Cscape. All right, and I'm going to go ahead and what I have here is I have an XL7 Model 3, which means that has two 12-bit 4 to 20 milliamp or two 12-bit 0 to 10 volt analog inputs built into it, and it's jumper configurable between voltage and current. So I'm going to go to the hardware configuration, which is here, configure hardware, local I/O. I'll click under config next to the I/O, go to module setup, and then analog in. And you'll see up here, of course, is where I can configure whether I want 4 to 20 milliamps or 0 to 10 volts for my input signal. Down here is where I can configure this filter constant that we're talking about today. And that filter constant can be set between a value of 0 and 7. So before we adjust this, let's take a look at at my OCS that I have configured here on my desk. And what we're looking at here is kind of a zoom in of a 4 to 20 milliamp signal that's being generated by my handy dandy I/O simulator that you see over to the left. That's been wired into the 2 milliamp inputs on my XL7, and I'm showing for the first analog input, I'm showing kind of a zoomed in value of that signal. Now it looks like it's jumping around quite a bit, but keep in mind I'm zoomed in pretty good. The total current I'm showing here on the screen is between 12 milliamps and 12.3 milliamps. So there's only a third of a milliamp of range shown on the screen. So it's jumping around a bit for sure, but not as much as you might think. Okay, but this is with no filtering whatsoever. Okay, so this is my raw signal, if you will. All right, let's go back to Cscape. Now let's go ahead and make an adjustment here. Now, for me personally as a controls engineer, keep in mind what we're doing with this filtering is we are balancing stability, which we get with more filtering, with response time, which we lose with more filtering. Okay, so a value of 7 is going to be the most stable but the slowest responding. A value of 1 is the least amount of filtering we can apply to get some benefit of filtering with only a little bit of loss of response time. So what I'm going to do here is I'm going to go ahead and set a nice default value, which is kind of a value that I like to use, a value of 3. So from 0 to 7, a value of 3. And I'm going to go ahead and make this change. And because this is effectively a change to the Cscape program, because remember, I'm changing the actual configuration in the unit, I'm actually going to have to download this change here. Now, Cscape is checking to see what has changed. It's seeing that it's something in the hardware configuration that's changed. So it's going to actually give me a warning and say, hey, are you sure what you've changed in the hardware configuration isn't going to cause you to lose communication with your controller halfway through the download, which we don't want to have happen. Now, what would cause that to occur? Well, if I made a change accidentally to my IP address, if I was programming over Ethernet or something of that nature, I could, midway through my download, I could accidentally lose my connection, which is not what I want to do. But that's not an issue here. I'm going to go ahead and go back to the graph that I showed you before. Okay, let me switch over to my OCS overhead view. Now you'll notice that the graph has started over again. And why is that? Well, in this case, I'm sampling my analog signal and my filtered value, or my analog signal, every 50 milliseconds. So I can't use a traditional retentive trend, which allows me to maintain values through a stop to run transition. I'm using the continuous scope feature, which is sampling every 50 milliseconds. So it should be obvious, though, from looking at this signal, how much we have narrowed down the swing and how much we've added stability to this signal. You know, before I added this filtering, it wasn't uncommon for us to get values, you know, a quadrant above or a quadrant below, or I guess whatever you want to call that screen quadrant there on my graph. It wasn't unusual to get values that occasionally would get up towards the top of the next quadrant or the bottom of the previous quadrant. As you can see here, we're hugging the center pretty well. We could make it more stable, but we would do that at the expense of response time. Now I've got a very narrow range here we're looking in at. So if I make an adjustment here, it's very possible I could go off the screen. Let me see if I can tweak this. Yeah, I've just tweaked the reading just a little bit, and you can see that I was able to make a change and it responds relatively quickly, but there is some lag there. But again, I think for a lot of applications, this is a good starting point for the whole, you know, responsiveness versus stability by just going with, you know, a moderate value of digital filtering, let's say a value of 3, which I've done here. So that shows you how easy it is just to take advantage of the low pass filter that's built into the I/O configuration in every OCS. And you can, after making that one adjustment, you can allow the OCS's firmware to take care of the filtering for you. However, some of you may want to do things a little more sophisticated fashion. You may want to try other approaches. So let's go through what some of the other options are as well. Back to our content here. All right, next let's talk about the moving average type approach to filtering. And this is kind of the most intuitive, right? I want to filter my analog signal, so why don't I just average the previous X number of samples, average those together with equal weight, and I'll come up with an average value, and then that should be more stable than if I'm just looking at the analog value directly, right? So on the screen there, you can see in the upper right-hand corner, I'm showing, you know, kind of a data representation of what we're talking about there, where you've got maybe the last 10 values, you know, store them away every scan of your analog input. And at the bottom there, just a simple average calculation where you are going to sum up on every scan, you're going to sum up the analog value for the last 10 scans, divide that by the number of samples, and you've got an average. Okay, very straightforward. Now, in this case, you're going to need to involve logic. And again, with this approach, every sample has equal weight. Now, with the built-in low-pass filter with the OCS that we just reviewed previously, the weight actually is always greater for the previous value, depending on what level of filter constant you use. Whereas in this case, to add more or less filtering, you basically sample or maintain more or less samples that you're averaging together. But each individual sample will have equal weight with all the other samples. Okay, so that is just kind of a moving average type approach. Again, the most intuitive to think about probably mentally. Okay, so let's go ahead and illustrate or show you in Cscape how we might implement a moving average type filtering approach. Okay, so back to Cscape. Okay, so we're back to Cscape. Now, what I've done here, and keep in mind I'm using advanced ladder variable based as my control logic here within Cscape for this project, what I've done is I've created a user-defined function block that performs the averaging for me. Okay, and this user-defined function block, the way I've designed it at least, it has one input and one output. The input is the integer value of the analog input that I'm going to be filtering. Okay, so this particular variable is tied to %AI1 for this particular case. Down here in this second instance of the same UDFB, I've got another analog variable that's tied to %AI2. Okay. Now, in addition to the input, that's an integer, that's the analog signal coming in, I've got another integer going out, which is my filtered value. Okay. And then the other input to my UDFB is the number of samples that I'm going to maintain in an array and the number of samples that I'm going to average together to come up with this filtered value. So that's what we've got here. So that's the beauty of UDFBs. Once you've created them, you just plug in your inputs and your output variables, okay? And you can have multiple instances of it, just like I've shown here. Now, just to show you how I accomplish this in logic, let's go ahead and take a look at the logic within the UDFB here. Okay, so to kind of get things started, what we are doing is, because of the fact that we're going to be creating an array, in this logic at least, creating an array of the last 100 values of analog input readings, because of that, I need to do everything in this subroutine either in double integer math or in floating point math. And I've decided to go ahead and do it in floating point math, or real values. So I start off with taking my analog input that was passed to the function or passed to the UDFB, and I convert and create a new variable that's a real equivalent of that. Next, I have a couple things that I do on the first scan. Now, what this UDFB does is it effectively maintains an array of the last 100 analog input scans for that analog input variable. Well, what happens right after power up or right after we go into run mode? Well, what happens is we don't have the last 100 values to deal with. So what we have is we need to build our array or fill our array in on the first 100 scans of the first 100 conversions. So on the very first scan, all we can really do is take the analog input conversion that we just received and pass it directly as the output to the function, or the output of the UDFB. Okay, because we've only got one to compare it with. We don't have 99 other readings to compare it with. Okay, so this is just a little bit of housekeeping, or what we do on the first scan. And then everything else in this UDFB is executed when it's not the first scan, so every subsequent scan after that. So the first thing we're going to do is we're going to, because we want to maintain an array of 100 of the last 100 analog input values, we need to count up on the first 100 scans to effectively ensure that we have our 100 values coming in. Because when we actually go to do our calculation, the number of values in our array is going to be important. Now, as we execute every scan and we receive a new analog input value in, they get loaded in this shift register. Okay, and this shift register is a shift register of real values. The input to the shift register is the real equivalent of our analog input conversion. All right. The array itself is referenced here, and that's our sample array. That's 100 long. And when we shift in a new value, we're going to shift in one position. So that's how we've got our shift register configured. Our direction is always shifting values up, which is left. And so this is the rung that just takes care of the shifting. Now, the way we're going to go ahead and do our average calculation is we're going to utilize a loop actually within this UDFB. And you can use loops in ladder logic. You just have to be really careful and make sure they're really well tested so that you don't end up with some sort of infinite loop. But I've thoroughly tested this and it works really well. So to set up our loop action, effectively, the first thing we have to do is determine how many times are we going to work our way through the loop. And by default, the number of times we're going to work our way through the loop is the number of samples that we were told to average. So if the routine was passed or the UDFB input was told we want to average the last 20 samples, then this variable here is going to have a value of 20. So by default, we would write that 20 to this max variable, and that's the number of times we're going to work our way through the loop. Now, the only exception to that is the first 19 scans through the logic in this example, we don't have 20 values that we can add together. We only have somewhere less than that. So in that scenario, instead of going through the loop the full 20 times or the full 100 times, we're going to only go through the loop for the number of values that are actually in our array. Okay? But once we get to 100 values, then we don't ever have to worry about that again. All right, then the last kind of bit of housekeeping we do before we execute the loop is we have to subtract 1 from the number of times that we're going to work our way through the loop. That's effectively the offset we're going to use when we're pulling analog values from our array. And why are we pulling analog values from our array? Because we need to add them all together and then divide them by a numerator to come up with our average. We're going to set a loop counter to 0. We're going to set our numerator to 0 because we'll start adding numbers to that numerator, but it needs to start at 0 and end up at our total sum. And then we also then are going to create our denominator variable, which is based on the number of times we're working our way through the loop. Okay, so at the very end of this thing, we're going to have a numerator, which is the sum of all of our analog input values, and we're going to have a denominator, which is the number of numbers we added together. We're going to divide those two, and that's going to be our average. Okay, and then here's what we have going on in the loop. All right, effectively, this is the indirect move where we are pulling out each analog input value one at a time as we go through the loop. That gets copied to a variable that gets added to the numerator. All right, and then we increment our loop counter. We check to see if our loop counter has reached max yet. If it has not, we do a jump back to the start of the loop. Okay? If it has reached its maximum value, it means we've gone through the loop as many times as we need. Then it's just a matter of doing our division of our numerator divided by our denominator, and then converting our real result into an integer value, which is effectively the output of our UDFB. Okay, so I know I kind of gave a really heavily detailed description of how I wrote this logic to do the averaging, but it does a couple things. One is it shows you one technique you can use, and the other thing, it shows you just how darn useful UDFBs can be. Okay, because after I've done this logic once and tested this logic once, I can then use it as many times as I need for my analog inputs, and I can even apply different number of samples to each of these instances of the UDFB. So maybe for one analog variable, I'm only going to average the last 10, another analog input variable average the last 50, etc., etc. Okay, so that's what it looks like from a programming standpoint. Let's go back and take a look at what it might look like from a real-time standpoint. Now, before I do that, I do need to really illustrate the functionality, or the impact, I should say, of the averaging technique I'm showing here. I really need to go back in and reset our filtering, our low-pass filter, to its disabled value of 0. Okay, so I'm going to go ahead and download this now disabled low-pass filter so that I can truly show you the impact of the averaging technique that I just did. Okay, so we'll have to, again, what's happening here in the background, the OCS is calculating what's different. It figures out it's in the IO configuration. It's going to give me a warning. We're going to do the download anyway, and then we'll be ready to show you what the impact was on the averaging. One thing I want to mention is that the topic for this particular live stream came from a customer. So we love to get suggestions for live streams so that we can give you guys topics that you want to see. So don't hesitate in the comment section, and email, on our website, wherever you can provide us feedback. Don't hesitate to make suggestions for new topics, and we'll do our best to get them implemented quickly. So now let's go back and take a look at our OCS. There's my main menu here. Now I'm going to go ahead and take a look at the graph for the second analog input. And the second analog input is actually one of the ones here that I'm showing you in the top graph. That's the raw analog input value coming in from the AI register and mapped directly to an input variable. On the graph below, I'm showing you the result of doing a averaging of the last 10 readings. So you can see significant improvement in the stability of the signal just doing 10 readings. Now I'm going to go ahead and go back and change that value to 100 just to show you. Now it's going to significantly impact the ability for the signal to respond quickly. Okay, so there's no free lunch here. We're getting added stability as a result of lower response time or slower response time, but in some applications that's perfectly fine. The analog signal is changing very slowly anyway, so stability is really what we're after. And you can see just after a few seconds here on the screen that you can really, if your signal is otherwise looking pretty good, it's just a little bit unstable, you can certainly greatly enhance that through averaging as well. So next I'd like to go back and let's cover a little bit more material, talk about some of the other techniques that we can use. Okay, the next technique I'm going to talk about in terms of filtering analog signals is I'm going to talk about limiting. And with this approach, really what we're talking about is limiting the step response for any one particular reading that we will allow to occur. So it's that big jump that occurs that we want to really knock down so it doesn't take quite that big of a jump. Because the big jump could be noise, or the big jump could also be a fast responding signal. So by using the limit technique, what we're going to do is we're going to effectively establish what's the maximum instantaneous change in reading that we're going to allow. And then every time we do a reading, or take a look at the current analog input value, we're going to compare it against our current average or the current filtered value, and we're going to see what the delta is between those two values. And if that delta is greater than the maximum that we've decided to allow, then we're going to limit our newly filtered value to only change by the amount that we've established as being maximum. So over on the right there, I'm showing you kind of the equation you can look at where y sub n is your new filtered value. Y sub n minus 1 is the previous filtered value. And then delta V sub n is the change in value for the current reading. And what is that delta V for the current reading? Well, it's the difference between our current reading, which is x sub n, and the previous average or previous filtered value. Okay? And again, we check to see if that delta Vn is greater than our delta V max. If it is, then we limit delta Vn to be equal to delta V max. Okay, so by going through this technique, you can knock off those quick transient responses without losing some of your ability to respond to a step change. Okay, so this is another technique that you can use, and I haven't implemented it here in Logic, but I wanted to tell you about it. Next, I want to talk about some really advanced approaches that you could take, and specifically a filter that's really popular in analog design, and that is a Butterworth filter. And it was named after a gentleman, I think it was invented back in maybe the early part of the 19th century, maybe 1930 or so, kind of back in the radio design days. But what is a Butterworth filter? Well, a Butterworth filter is a technique which is, first of all, it's a much more sophisticated filter that's based on some advanced math. And what it did was it improved upon previous filters that were available then and are still available today, which can attenuate a signal. However, they have the side effect of causing ripple in the signal that you do want. So they do attenuate the signal you don't want, but some of these other filters added ripple to the signal that you do want. And one of the things that's great about the Butterworth filter, and it's the one there shown on the screen in green, is it basically gives you a nice sharp knee or cutoff point, minus 20 dB, minus 40 dB, depending on the order of the signal, of the order of the filter. But it doesn't have any of those rippling that you see in some of the other filters, such as the elliptic filter or the Chebyshev filter, for instance. So the Butterworth filter definitely has some advantages. Now you say as well, how am I going to implement something like that in an OCS or a PLC? Well, keep in mind the OCS supports advanced math, so it's perfectly logical or capable of handling the types of calculations that are required for a Butterworth filter. So courtesy of Peter Natchway here from Delta Computer Systems, he was kind enough to post his details on implementing a Butterworth filter in a device like a PLC or an OCS. At the top there, you've got Y sub n, which is effectively your filtered value that you're going to calculate. And you can see that filtered value is based upon the last couple of filtered values that were previously calculated. So you need to maintain those in your OCS memory as well. And then it's also based on X sub n, which is your current analog reading, okay, your new conversion, if you will. And all of those values have coefficients associated with them. And what are those coefficients? Well, you can calculate those coefficients. They're shown there in the box. And yeah, there's a lot of Greek letters there, which can add sweat to our brow as we look at how we calculate those. But really what those Greek variables are all about is your cutoff frequency. What frequency do you want that cutoff, or that 20 dB or 40 dB of attenuation? What's your sample rate? How often in seconds are you sampling a new value? And if you're talking about an OCS that's running at a typical 5 millisecond scan rate, and you're talking about a model 2, 3, 4, 5 type analog I/O, then whatever your scan rate is pretty much is going to be your sample rate. If you're talking about the Model 6 sample rate is slower than that, so you would plug that sample rate in as well. And after cranking through those calculations, you could very easily, in OCS logic, create a UDFB, which has a configurable cutoff frequency and a configurable sample rate, and would effectively apply, let's say, a second order Butterworth filter to an analog input signal. And then again, you would have the benefit of good attenuation with stable signal in the area that you don't want to change, and you'd have a lot more precision in that filtering than you might have with some of these other techniques we've shown. So that is the Butterworth filter, for instance. Okay, so that's the material that I wanted to share with you today. So I'm going to take the opportunity now to bring Casey Gardner back in. Okay, Casey, so I assume you saw some things there that made some sense to you. Have you had a chance to do much with UDFBs yet? I found them really, really awesome when I've used them in my recent programming.
Just a little bit, but I would agree. I mean, in certain examples, they can take a number of minutes or hours of programming out of the equation to make it much easier to just kind of copy and paste kind of.
Absolutely. The other thing I love about the UDFBs is that you can reuse them over and over again from project to project. So I didn't show how you can save that UDFB away as a separate file and then bring it into another project, but that can be done easily. It's very, very straightforward. Okay, any questions today
absolutely.
from the crowd?
We had a couple.
Okay.
A couple different sources from YouTube. We had one regarding if we could do a Kalman filter,
okay.
Which I don't believe we have necessarily a native filter option, but it would probably be something we could put together in logic similar to what you did with the Butterworth, correct?
Sure. Now, I haven't actually implemented either the limit filter or the Butterworth filter, but I plan to. I've got that down on my to-do list just because I had a lot of fun doing the averaging filter, and I want to do some more UDFB programming. But yeah, we don't have that available today, but certainly if it's, I don't see any reason why we couldn't implement that. Now, obviously, in a perfect world, it would be nice if we had, programming functions already available in Cscape or maybe built into firmware that did some of these advanced filters. And I think that will happen over time. In the short term, though, it's nice to be able to implement these with a little bit of programming in a UDFB. So we'll definitely get that added to the list and see if we can get an example of how to implement that.
Absolutely. And then I think, let's see here. we had a comment from Mark, who actually kind of gave us an example. He said he uses calculated moving average filter called at 100 millisecond intervals, and then he actually copied, it looks like it's in structured text.
Nice.
He copied in an equation for us.
Outstanding.
So that was just an example. He's using filtering techniques as well.
You're right. And Mark's using structured text. So that is obviously an option in the OCS when you're using our IEC languages or our enhanced IEC languages, which are the same thing, just with some extra features. And I know that Mark and his crew are experts in those languages, and I'm really looking forward to, maybe December or maybe January, we're going to have a whole series in this forum on the different IEC languages and the IEC programming that's available in the OCS. We've covered it a little bit in the past with one or two live streams, but this will be some really nice hands-on, and we're going to get in front of the IEC and enhanced IEC options for the OCS and give some good examples on getting started and different languages to use and those sorts of things. And from my perspective, certainly structured text is my favorite language when we're talking IEC. Okay, thanks a bunch, Casey. And again, we'll get those addressed, or at least that first question on that first filter, we'll get that addressed with a future example for sure. Okay, let's go back and remind everybody that we're here every Tuesday at 2 o'clock. Here live on YouTube as well as live on Big Marker, with the opportunity for you to ask live questions and get those answered. If you're watching these on replay, which is another great option, again, don't forget to ask your questions. Just do so in the comment section for sure. All right. And I will remind you again, our number of subscribers is growing nicely and has for all of 2021, as we've managed to release a new video every week, most of them being live. So for those of you who haven't already subscribed, I would suggest that you do so. It'll help you get notifications when new videos go online. It'll also help suggest to you when we have new videos appear. Okay, so I want to remind you that next week, our topic is hands-on with Ethernet Global Data Protocol. Now, our Ethernet protocol live streams have been some of our most popular. Certainly the ones for Modbus TCP and Ethernet IP and BACnet IP have been extremely popular. Ethernet Global Data is a protocol that a lot of people don't necessarily know that much about, but it's extremely useful, especially for moving large chunks of data, variables typically, from one OCS to another in those applications where you may have multiple OCSs involved. So we're going to get hands-on with Ethernet Global Data next week. Once again, thanks for joining us, and we look forward to seeing you next week. Stay safe out there.